hundreds of millions of years ago, nature carved the Earth into continents, pushing Asia almost to the edge of North America, leaving only 55 miles of frigid ocean between them. Called the Bering Strait, this is one of the most desolate places on Earth. In winter, wind chills drop to 100 below. It's an environment utterly hostile to human life. But if one visionary engineer has his way, someday the crew of a lonely oil tanker in the strait will look up with awe as they pass under one of the most massive structures ever built. A bridge joining continents. A bridge so long it would be, like the Great Wall of China, visible to the astronauts in space. But could engineers actually build it? Could it survive the worst of nature's fury? Can man finish what nature began? Connect two vast continents across the Bering Strait? A bridge across the Bering Strait? Not long ago, the idea would have been laughed at. A bridge across the Bering Strait would rank among the most daring projects ever attempted. Right from the start, the project would face two enormous obstacles. First, no bridge even close to its magnitude has ever been designed, let alone attempted. And second, even if the bridge can be built, the severe conditions here just below the Arctic Circle would almost certainly destroy it. The Bering Strait is a deadly body of water. 8 months a year, it is choked with monster ice flows, some as high as houses. And that's not all. The bone-numbing temperatures and howling winds can make just being outside deadly. During the Cold War, the Bering Strait served as a dividing line, separating the two great superpowers. So a bridge would symbolize a new era of friendship and create vast new opportunities. By connecting Asia with North America, the Bering Strait Bridge could be a critical link in the proposed global highway, which would allow people to drive literally around the world. And there's another reason to build the bridge. Siberia holds vast oil and natural gas reserves. Connecting that huge supply with America's insatiable demand could greatly reduce America's dependence on the Mideast. Of course, the idea of a bridge across the Bering Strait is nothing new. 20,000 years ago, during the last ice age, dramatically lower sea levels created a land bridge across the strait. It lasted just a few thousand years, but long enough to provide early man's gateway to the Western Hemisphere. And now, the world's most famous bridge builder proposes to reopen that route with a man-made bridge. A bridge bridge that would soar 200 feet above killer ice flows. A bridge that would leap 55 miles across the sea, the equivalent of crossing the Golden Gate Bridge 32 times, allowing cars to drive from Alaska to Siberia in less than an hour. But since the bridge would straddle the international date line, a driver starting on the Alaskan side would get to the other side at almost the same time he left, the next day. The plans for such an ambitious project have taken more than 30 years to complete. They are the brainchild of T.Y. Lin, the world's greatest bridge builder. First conceived to promote cooperation during the Cold War, the Bering Strait Bridge would in fact transform the world.
You see, a bridge is a symbol. People can see it. You know the old Bible saying, "Where there is no vision, the people perish."
Lin's bridge would not just bring people together, it would revolutionize the world economy. It would provide a pipeline for Siberia's precious oil and natural gas reserves direct to Western refineries, heating homes and filling gas tanks from Seattle to Santiago. It would also carry high-speed trains between the United States, Canada, and Russia. But could such a vast bridge ever really be built? It would be perhaps the most challenging construction project in human history. Construction teams would need to work around the clock. Most bridges have 2 piers or support towers. Lin's mega bridge would need 220, some the size of 40-story buildings. They would support 220 separate spans, many as long as 6 football fields. The design calls for 3 separate levels stacked on top of each other. On top, a 2-lane open roadway for cars and trucks. A middle level for high-speed trains. And a third for oil and gas pipelines. The lower levels would need to be completely enclosed against the ferocious 8-month winters. The top deck could open to traffic only during the brief summer. Ben Gerwick is a world-class engineer who helped design the bridge. Even he was skeptical at first.
When I first heard about this bridge from T.Y. and he was talking, I thought, this time, T.Y., you've gone too far. It's impossible.
Does any existing bridge even approach the scale of the Bering Strait Bridge? The longest bridge in the world today is the Lake Pontchartrain Causeway outside New Orleans. It's 24 miles long. And the causeway crosses calm waters in a temperate climate. A world away from the violent seas and Arctic conditions at the Bering Strait. Engineer Albert Ockel also consulted on the Bering Strait Bridge. He too was skeptical.
You're talking about a location which is a few degrees below the Arctic Circle. So all the temperature conditions, the ice conditions that prevail in the Arctic Circle are present there. The winds are so strong that they could blow a truck off of the bridge. It's that bad.
The area around the strait is one of the most desolate places on Earth. The Alaska side is almost totally barren. In such a bleak environment, simple survival is a challenge.
You know, that land up there is just nothing but marshes. It's lakes after lake after lake, interrupted by some very small bands of tundra.
There are no highways, no railroads, no major flights. factories, construction yards, or suppliers. The few villages are tiny and far apart. The nearest town of any size is almost 100 miles away. And the Siberian side is even more remote. So by itself, the Bering Strait Bridge would lead from nowhere to nowhere. That's why the plans call for thousands of miles of new highways and rail lines leading up to the bridge from both sides. This new Arctic corridor would span 4,000 miles, from central Siberia to southern Canada. That's the same distance as Chicago to London. It would link the great population centers of Europe and Asia with those of the United States and the Western Hemisphere.
It would be a very large commitment, and probably the cost of those connections would be many times, maybe 3 to 4 times of what the bridge itself would cost.
That cost could reach $105 billion, 5 times the gross national product of many small nations. Would such a vast investment be worth it? Earlier projects may offer clues. Construction on the Trans-Alaskan Pipeline began in the 1970s. The pipeline runs 800 miles through some of the world's most forbidding terrain and crosses 3 mountain ranges before ending up at the port of Valdez on Alaska's south coast. But it begins in Prudhoe Bay, 600 miles north of the Bering Strait. Weather conditions here are extreme. Wind chills can plunge to 135 degrees below. A human being without proper protection could die out here in less than a minute. Before work could begin on the pipeline, the infrastructure had to be built. Access roads, landing strips, and housing for thousands of workers. Over 500,000 tons of steel pipe were shipped in. Work went on around the clock for 3 years at a final cost of $8 billion. Today, nearly 1 million barrels of crude oil and natural gas flow through the pipeline every day. But a Bering Strait bridge would be far more costly, far more difficult to build than even the Alaska pipeline. Its designers would need to solve an enormous problem, one the pipeline builders didn't face. Ice. In the form of massive glaciers, ice carved out and shaped our valleys, mountain ranges, and lakes. In the Bering Strait, the threat comes from huge ice floes barreling through the frigid waters. The flows become most deadly in the spring, when thick, solid sheets begin to melt, breaking up into immense, fast-moving blocks. In the 1940s, an assault of crushing ice floes destroyed 3 bridges in Warsaw, Poland. The unrelenting ice, more than 3 feet thick, battered the bridge's piers until they finally buckled. In the Bering Strait, the flows are even more powerful and much more destructive because they come from the ocean, where the slabs have room to grow to monster proportions. Engineer Alan Christofferson has been observing the raw power of ocean ice for more than 25 years.
When ice hits a structure, Often the pieces are so large and so heavy, it can be like large ships running into the piles and the structures. I mean, it is that strong.
In 1986, giant blocks of ice began to pound against an oil platform like this one off the coast of Canada. The platform shook so violently, helicopters had to evacuate the crew. And ice in the Bering Strait can be even more destructive. The strait acts like a funnel. Charging down from the Arctic, the ice is compressed into mega ice flows that accelerate through the narrow channel with the force of a freight train. Fierce winds and currents mash the giant ice packs together, driving thousands of tons of ice upward into mini mountain ranges called pressure ridges. Some as big as entire blocks of row houses. Could any bridge withstand this kind of beating? Until recently, there was no way to answer that question. Then in 1994, a Canadian team began to work on a bridge connecting the mainland to Prince Edward Island across the Northumberland Strait. The 8-mile-long Confederation Bridge opened in 1997. Today, it is the world's longest bridge over ice-covered waters. The Confederation Bridge builders confronted many of the same problems that would face the builders of the Bering Strait Bridge. But Ross Gilmore, chief design engineer of the Confederation Bridge, knows there's one critical difference.
The factors that we dealt with are all the same ones that would have to be dealt with on the bridge across the Bering Strait. Only there, everything would be taken to order of magnitude higher, further, longer, more remote, more expensive.
Conditions in the Northumberland Strait are plenty severe.
Unlike what we see behind us now, where we have clear blue skies and blue water and nice sunny days, during the wintertime it can be quite a formidable place. The strait will block up completely with ice.
During the winter, hundreds of tons of solid ice slam directly into these piers. And if just one pier was damaged, a whole section of the bridge could collapse. The engineers needed to design piers that could stand up to that kind of punishment.
What we're showing here is a ridge interacting with the Confederation Bridge. So on the third pier here, we can see that the ridge is actually pushing the pier over, magnified many, many times.
The Confederation Bridge engineers used computer models to analyze new designs. Smaller bridges had been built over icy waters before, but none that approached the size of the Confederation Bridge.
Sure, there are bridges across rivers in towns, but those are small bridges and subject to ice conditions which are pretty easily understood.
But ocean ice is far more dangerous and far less predictable, according to ice expert Tom Brown.
You're building a bridge on the ocean, you're building and having to deal then with the ice conditions in the ocean. Much more difficult question, much less well understood question as well.
No bridge piers had ever been built to withstand these conditions. So there were no real-world models to test. They'd have to do their own tests under the proper conditions. Pier designs are tested in enormous temperature-controlled ice chambers like this one. This test basin holds up to 250,000 gallons of water, the equivalent of 10 swimming pools. It's so cold in here that water vapor condenses and actually falls as snow.
Is this pretty good seeding down there?
Though the ice is less than 2 inches thick, it responds very much like 5-foot thick ocean ice.
is thick.
To test a pier design, engineers first attach a scale model to the blue steel holder that will push it across the ice. The design being tested here is a simple vertical pier, standard on many bridges around the world.
Start the carriage.
Here in the lab, the ice doesn't move, so they move the pier instead. The ice impacts the model just like it would if this was a full-scale pier. And now, engineers can measure it. When the ice strikes this model, it is first compressed, then crushed into pieces. The full force of the impact is absorbed directly by the pier. So the model shakes violently. That much vibration could be disastrous for a real bridge. This is a real bridge. It's a view looking down a 100-foot pier on a bridge in Alaska. This bridge shakes like a carnival ride during ice season. Another solution would have to be found.
When some tests were done for the piers for Confederation Bridge, they originally did look at vertical piers. And quite frankly, the results scared the designers.
Vertical piers would be dangerous in the Bering Strait. The much larger ice slabs would slam the towers with far greater force. An alternative was desperately needed. The Bering Strait Bridge would need to somehow withstand the onslaught of ice. The solution was inspired not by another bridge, but by something else entirely. Something built to confront massive sheets of ice head-on. Ice-breaking ships. Icebreakers don't actually crush the ice. Instead, they ride over it. Their wedge-shaped hulls and enormous weight, bending and breaking the thick slabs, pushing the great hunks of ice down under the surface and out of their way. In this way, icebreakers create open channels through otherwise impenetrable sheets of ice. Confederation Bridge engineers wondered, could they somehow adapt icebreaker technology for their piers? They went back to the lab to test a new design. A cone-shaped pier, resembling the bow of an icebreaker turned upside down.
There we go.
Here, the ice sheet rides up the cone, and the ice actually bends, then breaks apart. The full force of the impact dissipates, and the pressure against the pier is cut in half. As a result, Confederation Bridge engineers designed all 44 piers with a conical wedge shape at the surface. They function, in effect, like 44 anchored icebreakers. On the Bering Strait Bridge, the piers would also be conical. Of course, there would be more than 5 times as many. So the shaking problem seemed to be solved. Battered by ice forces twice as strong as those found at the Confederation Bridge. And the piers would need to support a heavy 55-mile-long road deck. To do their job, the piers would need to weigh 50,000 tons each, 5 times the weight of the Confederation Bridge piers. Could such massive structures even be built? The answer to that question lies half a world away. The Gulf of Corinth separates the mainland of Greece from the Peloponnesian Peninsula. In 1999, construction began on a bridge that will cross the Gulf. The Rion and Tyrion Bridge will extend an impressive 2 miles from end to end. And it will be held up by the largest piers ever built, each weighing 100,000 tons and nearly as tall as the 968-foot Eiffel Tower. At 300 feet in diameter, these enormous towers would cover an entire football field. Engineers here certainly don't have to worry about ice, but their bridge must be strong enough to withstand another equally terrifying force of nature: earthquakes.
Almost 1,000 persons died when these buildings crumbled, and 130,000 are homeless in the worst quakes in modern Greek history.
In 1995, an earthquake here measured a catastrophic 6.5 on the Richter scale. But the Rion and Tyrion Bridge has been designed to withstand far worse. The concept is simple: massive weight and size.
Yes. Yeah. When the pier is shaken by a big earthquake, they are stable because they are very heavy, they are massive, they are large, and by their own weight, they can bear this shaking, and they cannot overturn.
Just erecting these giants was a mammoth undertaking. Engineers determined that the bridge could now survive a cataclysmic earthquake as high as 7.0 on the Richter scale, 5 times stronger than the 1995 quake. But construction techniques weren't the only valuable lessons for Bering Strait engineers. They'd also be using many of the same materials. One of the most important is a lightweight, high-strength steel reinforcement rod, known as rebar. Bending and welding these bars together, workers on the Rion and Tyrion Bridge first construct a skeleton of the entire structure. More than 70,000 tons of rebar will go into the finished bridge. The Bering Strait Bridge would use 10 times as much, almost 750,000 tons. That's enough rebar to reach from Earth to the moon. To the untrained eye, concrete looks like, well, concrete. But the super concrete used for bridges is made from high-tech ingredients, and each batch is custom formulated for the specific needs of a particular bridge. Ordinary concrete, a simple mix of cement, water, and stones, isn't strong enough to withstand even a moderate earthquake. So like chefs concocting a new dish, engineers mix a variety of chemicals for maximum strength.
High-strength concrete is really as delicate as high cuisine, you know, because you have to put a little bit of this product, a little bit of that product. You try it, there is not enough, you put a little bit more.
If preparing the right concrete is like cooking a gourmet meal, then laboratories like this are 5-star kitchens. engineers at Chicago's Construction Technology Laboratories are testing a new concrete recipe to determine how much weight it can support. Increasing amounts of pressure are applied to a 25-pound sample.
A little more.
It begins at 100,000 pounds, about the weight of 35 full-sized cars. Then 200,000 pounds, the weight of a fully loaded jetliner. 300,000 pounds. 400,000. The concrete for the Bering Strait Bridge will have to pass another critical test. Some of the most extreme temperature variations on the planet. To simulate that harsh environment, researchers place samples in a freezer that chills them to 0 degrees Fahrenheit. After 2 hours, the sample is warmed back up to room temperature, then frozen again. These cycles of freezing and thawing are repeated 6 times a day for 2 months. Every 5 days, engineers test for thermal damage. Tapping the sample with a small metal mallet sends sound waves to a computer that displays them as a graph. Engineers scour the graphs for the slightest anomalies or variations. Even the most minute changes can indicate that cracks have developed.
If the concrete's cracked, it allows the seawater that contains chlorides to get into the concrete and eventually get down to the level of the reinforcing steel. That can cause corrosion, and that can seriously jeopardize the longevity of a bridge.
Confederation Bridge engineers confronted the very same problems. They discovered that adding ashes left over from coal and steel production would greatly enhance the strength and durability of concrete. High-performance concretes are revolutionizing large-scale construction projects worldwide. Most conspicuously bridges, which are being built not only longer and stronger than ever, but even combining the perfect design with the perfect materials can't solve the single most formidable obstacle to building the Bering Strait Bridge.
The window of work in that location is 4 months a year, maximum 4 months a year, because of the ice sheet or the ice pack. The ice starts forming around October, November.
All work at the Bering Strait construction site would have to shut down for most of the year. Construction would take decades. Engineers on the Confederation Bridge faced a similar obstacle.
When you've got 2 meters of ice floes covering the strait, there's no amount of will or money or effort that's going to be able to circumvent that problem.
With pouring concrete on site impossible during the extreme winter months, engineers devised an entirely new way to build a bridge. In pieces. Pier foundations, shafts, and girders were constructed onshore year-round in a massive prefabrication yard. Each of the large pieces, like the massive girders, was composed of several smaller segments connected by bundles of cable. Workers threaded the heavy steel cables through each piece. At each end, heavy gripping machines grabbed the cables and pulled them tight, like stringing a tennis racket. The ultra-taut cables were then clamped off with large anchors. As the cables try to relax to pull back to their original length, they actually squeeze the concrete segments, making them denser and much stronger. Moving the pieces into place is a major undertaking. On the Confederation Bridge, the main girder alone weighed a staggering 8,250 tons, the equivalent of more than 4,000 SUVs. So one of the first challenges was to find a crane that could lift such massive weights. It had to be both immensely powerful and extremely mobile for maximum efficiency during the short summer construction window. Engineers found what they were looking for in Denmark and shipped it across the Atlantic to Canada. The Svanen is the world's largest self-propelled marine crane.
The size and the shape and the capacity of the Svanen is unprecedented. And this is what I used to term the space shuttle of construction.
Even so, the Svanen would sometimes require a full day to carry and position one of these gigantic pieces. Constructing the Bering Strait Bridge would require not one, but at least 5 self-propelled marine cranes like the Svanen, only bigger. It would be a huge undertaking and hugely complex. During the winter, construction would take place in prefabrication plants in cities like Anchorage, Alaska, and Tacoma, Washington. Then, in the short summer window, those pieces would be shipped up to the work sites. The bridge would consume enough concrete to build 140 Empire State Buildings and enough steel cable to wrap completely around the equator. Twice. But even if the bridge could be finished, its builders would still face another test. Every square foot of the Bering Strait Bridge will have to be continuously watched. Every inch of the piers and roadbed must be fail-safe, invulnerable to the violent assault of Arctic ice. A centralized system like this one at Confederation will help technicians track the single greatest threat. A network of sensors warns engineers when the ice force against the piers builds to dangerous levels. The key instrument is an ultra-sensitive tilt meter.
Actually, it looks like we're not seeing a lot of corrosion.
Installed in the hollow shaft of a pier, it measures exactly how much the tower leans under pressure from the ice.
This tilt meter is so sensitive that I can actually, if I actually push very gently on this steel panel backing it, I can actually measure that tilt, the tilt caused by my pressure.
A second monitoring system tracks the force of impact through a series of pressure panels, large red plates that attach just above and below the waterline. Video cameras also focus on the pier at water level, continuously recording how and in what patterns the ice pack is breaking up.
Bridge control, go ahead.
Just as crucial to safety are monitors that track traffic on the bridge and the weather. emergency crews stand by 24 hours a day. Call boxes are positioned every half mile. When a call comes in, the crews respond immediately.
Bridge control, go ahead.
Warning lights and automated signs keep motorists informed of changing conditions. All aspects of bridge operations are monitored and controlled from a central location. But even with the most sophisticated monitors and most meticulous construction in the world, designers of the Bering Strait Bridge still can't be sure how their bridge will handle a worst-case situation. And that disaster scenario might look something like this. It's springtime in the Bering Strait, when the ice is most dangerous. A 250,000-ton mountain of ice, 600 feet wide and solid as a rock, has entered the strait and is bearing down on the bridge, on course to crash head-on into its center pier. If the pier collapses, it could cause hundreds of deaths and ecological disaster. In the Operations Command Center, technicians are anxiously monitoring the ice mountain's path while desperately trying to clear the bridge. All emergency crews are on highest alert. It all comes down to the pier. Can it withstand a head-on collision with a mountain of ice weighing 250,000 tons? Violent shaking forces the train to an emergency stop. If the pipelines burst, it will send oil gushing into the Bering Sea. But if the bridge designers have done their homework well, and the conical piers work as predicted, the brunt of the impact will be deflected. T.Y. Lin and his fellow designers believe they have planned correctly for this scenario. But no one can know for certain until the bridge is built. That may not be for decades, if ever. And yet, a bridge across the Bering Strait may be an idea that's so powerful, it's inevitable. So one day in the future, a massive oil tanker might not seem much larger than an ordinary tugboat. As it cruises into the Bering Strait under a bridge so huge, it changed the very face of the Earth. Visionaries like T.Y. Lin and their dreams transform our world.
The structures once